All right, we will continue our unit on rational expressions and radical functions and all sorts of fun stuff. And we're getting into binomials now, where it's not only multiplication that's occurring. Now we're going to throw in some addition and subtraction and see how much I can confuse you. So don't take that personally, but we're going to work on some other stuff. So I have 3 examples here that should highlight some major concepts of this unit, and will enable you to practice in your homework and get really good at what you're doing. Again, just like before, we're going to jump right in. So we're going to simplify the first expression in number 1 and figure out how in the world is that going to be possible. Okay, so we have a couple of cube roots, and isn't that problematic? So a couple of cube roots, isn't that problematic? Now the only way we can add 2 things is by combining like terms. It's the only way we can add 2 things, is only if they're like. Okay, so remember, we can only combine like terms. Only combine like terms. Clearly, these are not like terms. We get the cube root of 54, the cube root of 16. That's not like at all. All right, so now we got to figure, can we create like terms? Is there any way we can simplify these terms? Can we simplify them? Because we're dealing with numbers and we're dealing with cube roots, maybe there's a way to simplify them. So we have to think, well, what are some numbers that we can play around with? So we get the cube root of 54. Are there any perfect cubes that go into 54? And you gotta think. You know, for me, if I'm going to do a think aloud right now, I'm looking at the 16 first. Are there any perfect cubes that go into the 16? Yeah, there are. Did you know 8 is a perfect cube? I hope so. So we're dealing with the cube root of 8 times 2 times x squared, right? And that's going to help me with the 54, because I know the cube root of 8 is 2, but I know the 2 is going to be left in the radical sign, which leads me to the 54, right? Again, I'm going to do a think aloud. If I look at the 54, and I know if I'm going to combine like terms, will I have a 2 in the radical? In order for me to have a 2 in the radical, I got to think, well, does 2 go into 54? Clearly it does. It ends in 4. It has to. Guess what? 54 divided by 2 is 27. Guess what 27 is? A perfect cube. So this actually is 27 times 2 times x squared. And that's going to enable me to simplify each thing. Okay, so the cube root of 27, we should know by now, is 3. So we have 3 times the cube root of 2x squared left. Okay, because the cube root of 27 is 3. 3 pops out. And then the 2 and the x squared stay in the radical sign because the index is 3. These can't escape. The index is 3. Escape. Again, I keep using that word. And so we're going to do the same thing with this term over here. I know the cube root of 8 is 2, so that pops out. And what's left inside? 2x squared. All right, so hopefully you are careful with leaving your indexes. Okay, be careful with the indexes. Careful, because that's a pretty important part. Okay, so I've simplified both, and then I have the plus sign in between, right? So guess what we have? We have like terms, right? So you remember this. If we have, 3a's plus 5a's, well, that gives us 8 what? 8a's. And if we have, 3/17 plus 5/17, what do we have? We have 8/17. Okay, so the same thing works with this. If we have 3 cube roots of 2x squareds plus 2 cube roots of 2x squareds, how many cube roots of 2x squareds do we have? We have 5 of them. So we can combine these. We can only combine like terms. These happen to be like, so we have successfully simplified the expression. Okay, that is the successfully simplified version of this expression. So we can simplify each, and we know we can combine like terms. We're going to be careful with our indexes to make sure that everything is okay to go, and we're going to be aware of how like terms work. Okay, so that's it for number 1. Yay. All right. Number 2. Now we're going to start messing with your day. All right, number 2. We're going to simplify this expression now. 2 times the square root of 5 plus 3 times the square root of 2 squared. How in the world can we even address that? Well, let's take a trip down memory lane. If we had x plus 4 squared, how did we address that? Right? That was x squared plus 8x plus 16. Or if you need to do it the long way, feel free. X plus 4 times x plus 4. X squared plus 4x plus 4x plus 16. Either way, we get to the same result. Okay, so we're using the distributive property or the FOIL method or what have you. And that is exactly what we're going to do here. Okay, so we can't add these, can't add them. So guess what we can do? Multiply these out as if they were binomials. Isn't that cool? So we could multiply these out as if they were binomials. So we have 2 root 5 plus 3 root 2 times 2 root 5 plus 3 root 2. And we can treat it just like we treated our binomials. Right? The first term, we'll have 2 root 5 times 2 root 5. And then the next term, we'll have positive 2 root 5 times 3 root 2. And then the inside terms, 3 root 2 times 2 root 5. And then the last terms, 3 root 2 times 3 root 2. Okay, so this looks kind of confusing. So remember, the first thing we did, 2 root 5 times 2 root 5, right here, first term. Boop. And then the outside terms, and then the inside terms, and then the last terms. And then we just do the same thing as we did with binomial, multiplying binomials. So the rest is just being careful, okay? So what's 2 root 5 times 2 root 5? Do you know? It's 4 times 5, right? 2 times 2 is 4. Root 5 times root 5 is 5. So you have to be careful with your symbols. You really have to be aware and careful with your symbols. And then we go to the second thing. 2 times 3 is 6. 6 times the square root of 5 times 2 is 10. So hopefully you see what properties we're using. And then we do the same thing over here. 3 times 2 is 6. 2 times 5 is 10. Be careful with the radicals. And then the last term. 3 times 3 is 9. And then 9 times 2, right? Square root of 2 times square root of 2 is 2. So far, so good. Hopefully you can see what just is happening. We're multiplying whole numbers, and we're multiplying radicals, and we're really using this law of exponent, right? The square root of a times the square root of b is equal to the square root of ab. We are using that law, and that's what's happening. So now we just simplify everything some more. So 4 times 5 is 20. 6 root 10 plus 6 root 10, that's 12 root 10. Right? 6 root 10s plus 6 root 10s, that's 12 root 10s. The root 10s doesn't change. And then 9 times 2 is 18. So all I have to do now, combine like terms. 20 and 18 is 38. 38 plus 12 root 10s. And we can go no further than that. Okay, so remember the difference between adding and multiplying. Okay, so we have to remember adding versus multiplying. And just be careful, and you'll be all right. Okay, just be careful, and you'll be all right. All right, so that's how we approach binomials like number 2. All right, number 3. I'm wondering if you can see what the game plan is. And remember, we can't have radicals in the denominator. Hopefully you remember that. We can't have radicals in the denominator. So we look at this craziness, and we see that, well, darn it, there's a radical in the denominator. Do you remember what we had to do when we dealt with imaginary numbers and complex numbers? So a trip down memory lane. If we had 3 over, 2 plus 7i, how did we deal with that 2 plus 7i? We needed a clever one. And the clever one was the conjugate of the denominator. Okay, so if the denominator is 2 plus 7i, we would have to multiply it by 2 minus 7i, so we can end up with a difference of squares. Right? We can end up with a difference of squares. That was the whole, like a big note from rationalizing imaginary denominators. That's coming back. That's coming back big time. Because take a look. If we multiply the denominator just by the square root of 3, and we distributed the square root of 3, we'd have 2 root 3 still in the denominator. Still radical in the denominator. Can't work. We have to come up with our clever one that deals with the conjugate of the denominator. So our clever one is the conjugate of the denominator. So if our denominator is 2 minus 3 root 3, guess what the clever one will consist of? 2 plus 3 root 3. And that's what we would have to multiply on the top as well. Okay, so hopefully you can see what is about to happen. So let's see what's going on. So in our numerator, we have 5 plus root 3 times 2 plus 3 root 3. In the denominator, we have 2 minus 3 root 3 times 2 plus 3 root 3. Let's take care of the denominator first. This will turn into a difference of squares. Right? So in the denominator, we have 2 times 2, which is 4, minus, right, 3 root 3 times 3 root 3. Wouldn't that be 9 times 3, or 27? So we have 4 minus 27, which will be negative 23 in a second. Okay, so hopefully you can see that's the purpose of multiplying by the conjugate, so we can get rid of the radical sign in the denominator. So that's how we handle the denominator. Now for the numerator, we do just like we did in number 2. All right, so we have 5 times 2, which is 10, and then 5 times 2 is 10. 5 times 3 root 3, 15 root 3. And then root 3 times 2, okay, is 2 root 3. And then root 3 times 3 root 3, 3 times 3. 3 times 3 is 9. Okay, so root 3 times root 3 is 3. 3 times the square root of 3 is 9. All right, so square root of 3 times the square root of 3. 3 times 3, 9. And now we just simplify everything and we are good to go. All right, so we have like terms in the numerator, yes? Yes. 10 plus 9 is 19. And then 15 root 3s and 2 root 3s, well, that's 17 root 3s. And that's going to be over 4 minus 27, or negative 23. And there is our simplified expression, totally kosher, no radicals in the denominator. And that's how we work with binomial rational expressions. The rest is practice, practice, practice. Okay, so that's the main concept. And if this is the first video you're watching all unit, bad start. Go back to a whole bunch of stuff. But this is a good enough place for you to understand some things. Thank you.